Hello everyone, welcome to problem solving tutorial. This is me Heath. Today we'll be learning Euclidean GCD algorithm. GCD between two numbers a and b is the largest number that can divide both a and b. So this definitely will be the common divisor of both a and b, and among all those common divisor it will be the largest. Now, how do we find the value of this GCD of A and B? Say between A and B, A is the largest. That means A is greater than B. Then we can run a loop that runs for B times, and for each iteration we will check if a number divides both A and B. If we find a Heath, well, we will start from B to 2 and to 1, and we will keep checking if a number divides both A and B. And if we find such a number, we will just terminate that loop. Since we are going backwards, the first Heath we get will be the largest common divisor, that is our GCD, greatest common divisor. So this will basically be like this. So if there is any number I such that a mod I equals 0 and b mod I equals 0, we'll just break right there. And make our GCD as I. Okay, so this can be an approach, but this loop runs for b times, and if the value of b is quite large, then it will be a lengthy process to find out the GCD of between two numbers. Here is what happens in Euclidean GCD. For any two number a and b, the value of GCD any two number a and b is basically, if value of b is equal to 0, then the GCD will be a itself. If it's not, then we will return the GCD of b and a mod b. That means if we are to find GCD between a and b, two numbers a and b, then we will check if the value of b is 0 or not. If it's 0, then we will return a as the GCD of a and b. And if it's not, then we will recursively call the GCD function again. This time we'll call it with b in place of a and a mod b in place of b. So let's check if this algorithm actually works. For example, if you want to find the GCD of 16 and 12, what happens after the first pass? Here b is not equal to 0. Here a is 16 and b is 12, and b is not equal to 0. So we'll go to this line and we will return GCD of b and a mod b. So we will call GCD of b, that is 12, and a mod b, that is 4. 16 mod 12 is 4. Then now for GCD of 12 and 4, b is not equal to 0, b is 4 and it's not equal to 0. So we won't return a. So we return GCD of b, that is 4, and a mod b, that is 12 mod 4, that is 0. So we will call GCD for 4 and 0. Now for GCD of 4 and 0, we can see that this condition is true, that is b is equal to 0, so we'll just return 4. That means for this part we'll return 4. For GCD 4 0, this function call will return 4, the value of a. 4 will go to here. For GCD 12 and 4, while we were return GCD 4 0, we were actually returning GCD 4, since we saw earlier from this part that GCD 4 0 is 4. Since we are returning GCD 4 0 for GCD 12 4 recursively, that means for 12 4 we are also returning 4. And same goes for GCD 16 12. That 4 will keep coming from GCD 4 0 to 12 4 and finally GCD 16 12. So the value of GCD 16 12 will be 4. Okay, so let's check that for another number. So as we can see that if we had used the brute force process that runs from b to 1, it would have taken 12 iterations to complete. At worst case, it would have taken 12 iterations to calculate the GCD. But if we use the Euclidean approach, however, it had taken only 3 iterations to 3 function call, recursive function calling to find the GCD. So let's check it for another number, another pair of number. Say we are trying to calculate the GCD of a very large number, say 35 and 8. So what happens for this? Since 8 is not equal to 0, and okay, since 8 is not equal to 0, we won't be returning the value of a. We'll go to this line and we'll return GCD of 8 and 35 mod 8, that is 3. Okay, for GCD 8 and 3, we'll be returning GCD 3 and 8 mod 3, that is 2. For GCD 3 and 2, we'll be returning GCD 2 and 3 mod 2, that is 1. For GCD 2 mod 1, we'll be returning GCD 1 and 0, since 2 mod 1 is 0. Well, for GCD 2 1, we will be calling GCD 1 and 0. So for GCD 1 0, we will return, since the value of b is now 0, we will return a, that is 1. This one will go from GCD 1 0 to GCD 2 1 to GCD 3 2 to GCD 8 3 and finally GCD 35 8. So the value of GCD 35 8 is 1. So I hope how the Euclidean GCD works is clear now. So that's all for now. Thanks for watching.